So I'm starting the lecture. Today we are starting with oscillations, and actually we simplify it into simple harmonic oscillations. Let me try. 这样子有声音吗？这样麦克风有声音吗？有。So it works. So finally we come to oscillations, and in my opinion we are really working on physics. Finally we really start with physics. We really start from looking at things with a physicist's point of view, and we start to build models for the cases in reality. We started to deal with everyday objects. We are open the door to real complex problems. All of these is starting with oscillations. 那我们今天开始要讲震荡。对我来讲呢，我觉得我们磨几集东摸西摸的，终于要进入物理的殿堂了。对我来讲，我会觉得从这章开始才是真正的物理学。那我们从震荡开始，然后呢，我们会从最简单的形式，就是简谐震荡开始讲，然后呢，会告诉大家我们要怎么样把简谐震荡这个模型应用在各种复杂多变的状况底下，我们要怎么样用简谐震荡去形容一种有现实感，就是用一种很有现实感的态度去面对我们生活中，或是研究中，或是开发中各种各样的物理问题。So let's get started. So here's just a recap about oscillations that we just mentioned a few lectures before. So we started with the springs, and the spring is attached to a mass, and it's oscillating, as you can see from the little movies on the screen. And first we start with the position of the mass. So you can see, first of all, we have to find the equilibrium position, which is x eq here on the screen. And it should be symmetric. And we have the maximum x maximum and the minus delta x maximum. That means the displacement, the maximum displacement on both sides, on two directions. And then we focus on the velocity of the mass. We can see that the velocity is 0 on the two ends of the oscillations. And when it's on the equilibrium position, that is the places where your mass have the maximum velocity. So it moves with the fastest speed when it's at the middle of the range. And then for the oscillations, on the equilibrium position, the acceleration is 0, because on that point, if you take the equilibrium position as a reference, and then you are changing the direction, actually, if you take it as a reference point, and the acceleration on the two sides of your oscillation, that is the point for direction change too. And you can see that the acceleration can be maximum, but with different directions, and the directions is indicated by the plus and minus. Okay, so that's it. And here are the components of the forces in this system. So we are using a spring, and that is something that you can apply Hooke's law. So this is the force spring, and this is minus kx, and k is the Hooke's constant. And then this is the equation of motion. So we have the mass, we have the acceleration. So ma, that is just equal to the force, and this should be equal to minus kx. And then you can rearrange your equation a little bit, so you find the relation between the acceleration and the position, and you see that here is something like a coefficient. This is for the this is the elastic constant, and then this is the mass. Okay, so now you get all the relations. And here are three key points. The first one is the force from the spring is the restoring force. So that is the force which drive your masses to come back to the equilibrium position. So that's the reason why we call it restoring force. Second point, the direction of force of spring. and x are opposite. So this is the second important point. The third one, the magnitude of f of spring is proportional to delta x. So that is represented by the Hooke's law. So here are the 3 key points in this system. And now we have to solve this equation to have a mathematical representation for x. 那我们现在开始，我们要解这个方程式，然后它的名字其实是叫偏微分方程式。等一下会跟大家说为什么叫偏微分方程式。那我们的目标是我们想要知道 x 的函数，就是 x 你要用一个数学方程式把它表示出来。那 x 到底是什么？ And now we are solving the partial differential equations. Differential equation is, so you can see that the acceleration on the x direction, we are in one dimension. So this is a one-dimensional problem. And the acceleration is the second derivative of position versus time. So you can see here. The position is the second derivative of, acceleration is the second derivative of position versus time. So you do derivative on x for 2 times, and then you have a relation here. So this is the position again, and here are the coefficients which are related to your system. And this is differentiation. And if you can see that, probably it's hard to see it right now. You can think about it that way. So x, it can be a function of many parameters. But now we focus on parameter time. So there are many parameters, but we just pick one. So that is the reason why we call it partial differential equation. Here are many parameters, but I am partially focused on one of the parameters. That's the reason why we call it partial differential equation. And here is a little trick. In order to make the derivation clean, we just simply set k over m as a new parameter called omega squared. Okay, so now this is our trick, and this is how we arrange these equations. And here's a little remark for solving partial differential equations. Sometimes we call it the art of making Ansatz, and Ansatz is German. It's in English it's called educated guess. So when you're solving partial differential equations, and actually it takes experiences and it takes creativity. You have to guess what might the solution be. Then you put the solution into your partial differential equation and see if it works, see if it matches the requirement of your partial differential equations. That's the reason why we call it the art of making Ansatz. So now our Ansatz, the question for our Ansatz is, if you look at the equation, you can see the second derivative of x is x itself, isn't it? So this is interesting. And what mathematical representation can it be? So this is the start of making an Ansatz. 我们现在要解偏微分方程式。那大家以后数学学得越来越多之后，那理科的同学就是学物理数学或应用数学，工科的同学就是学工程数学。那里面都会有一个非常重要的章节叫解偏微分方程式。那你面对的问题越来越多，你面对的维度越来越多，你就会发现解偏微分方程式它其实是一门拆解的艺术，可是没有像猜那么随性哈。我个人会觉得那个有一点像是你在经过很多经验、很多实务经验，还有很多人的创意集结起来，然后你会发现说，某一种形式的偏微分方程式。它有某一些形式的解 solution 可以套进去，而且可以满足那个偏微分方程式的一些规范。那么在数学里面有一个分支的人，他们就对这个非常的有兴趣，然后他们发展出很多经典的问题跟经典的解法。那基本上我们解偏微分方程式就是这些经典 case 的排列组合，每一个都非常的有趣。我个人还蛮喜欢偏微分方程式的。 好，那我们现在就从一个最简单的开始。我们现在的问题是说，你观察一下那个最后一条方程式，你把位置对时间微分2次之后，式子的右手边竟然又跑出位置了耶！差别只在于你多出一个欧米伽平方这样一个小小的常数。所以呢，那我们要猜一下，所以现在我们有哪些数学方程式可以符合这样子的规范呢？好，其中有一个就是 sine 跟 cosine function. So the sine and cosine function is one of the choice that we can choose. Here, this is just what I said, and we just make a educated guess. Educated 就是你拥有知识，然后基于那些知识你去做一个猜想，这个叫 educated guess。然后德文叫 Ansatz。我想对数学很有兴趣的同学应该还蛮常看到这个字的。So this is our ansatz. We just make a guess, probably. Our position as a function of time should be a cosine function with the amplitude called A. And omega, this is what I'll tell you what the physical meaning later, what the physical meaning is later, but now we just take it as a coefficient. And this is time, and here phi, and this is another constant here. And omega and phi, and they have their meaning in physics. But for the moment, let's just take it as something like a parameters. They should be there because of some mathematical laws. And why we choose cosine function? Because the derivative of cosine function is giving you minus sine x. And if you do derivative on sine x again, and then you get cosine x, and mind the minus sign here. 然后注意一下这边有一个复数。And I think it could be quite obvious for you why we have a constant phi here, right? Because when you do the first derivative on time, and the phi just disappear, and when you do the second derivative, then you don't see it anymore. And so you can see that it's just a constant here, and it should be there. If you don't put it there, and then your solution is not complete. Yeah, and the reason why a omega is right there, because when you do the derivative on x of omega t, then the omega here should get out of your equation. You have one omega, and then you do the second time of derivative, and another omega is coming out. So that's the reason why you set an omega here, to match the requirement for the omega squared coefficient here. Okay. So, and here is just the derivations that I just said. So when you do the first time of derivative, then you have the amplitude here, you have 1 omega here, you have the minus sign because of this, and your cosine is turning into sine function. You have the omega t plus phi in the sine. And then this is the second time of your derivative, so I just skipped the middle. You have the minus sign here, the omega squared, because omega is coming out of your sine one more time, and the amplitude, the cosine. Yeah, okay, so this is the detailed process when you do the second derivative. And then you see that x is equal to this one. When you do 2 times of derivative, and the x just come back to itself, and this is omega squared, and omega squared is this one, and amplitude depends on how you set the boundary condition. Okay, so this is a process of summarizing a problem and making ansatz, and finally check if your ansatz work or not. 那所以我们这2张投影片，我们走了一个还蛮复杂的流程。其实，第一个是你要先分析一下你的问题，你的问题里面有哪些必要的条件。第二步就是你要拆解，你要猜一下说，那我的解要是什么，然后可以去满足我的平稳方程式的要求。第三个，把你猜的解带进你的平稳方程式，看这2个属性合不合。所以等，我们一下子就做3件事情。 And this is how our solution look like in reality. So the position of your spring is the displacement in this picture. This is up and down, and it's moving in a way like a cosine function. A is the amplitude, and here, just as we just defined, the omega is k over m, and taking the square root of it. 好，那所以这就是我们刚才弄了一堆数学，然后在现实当中，这就会是你的解看起来的样子。它其实就是一个上下震荡或左右看你状况，然后它是一个往复运动。那么我们的 omega 这边呢，其实就是我们之前有在推导过程中我们自己去设定的，它是弹性系数除以指点的质量，然后开根号。Okay. And here we just get a little bit deeper into our solution and what is the so first let's analyze the shape of our curve. So then we are doing some definitions on how to describe waves. So here you can see that the solution for x is a cosine omega t plus phi. And you can see it from the graph here. So this is time, when time is going on, and this is the position of your particle, of your mass. And the plus a and minus a, this is amplitude. So a, this is amplitude. And you can see that when time is equal to t, a period, so this is a certain duration of time, your particle is going to the other side and return and coming back. And then we start another cycle which is exactly the same. So that's the reason why we call it a period. So we set it as a capital T. This is a period. Okay. And sometimes when we are looking at the parameters in cosine function, we call it the phase. And this is a little bit, this is a new word, and sometimes it could be a little bit difficult for you, but you can just think about it as a cycle. And you can see that the cosine function is cyclic. So, cyclic. This is what I meant. So, a cosine, a omega t plus phi, and sometimes we call it phase. And you can think about it like when the phase is running from 0 to pi, so then you just finish the cycle. And the omega, sometimes now we can call it the angular frequency. So this is an angle, and the angle multiplied by time plus a phase shift is the total phase. And the phi here, this one, this is called phase shift, 相位差。通常大家是一讲到相跟相位差的时候，因为对大家来讲比较陌生，所以你常一听到相，然后就会放空。所以大家就是请习惯，就是请大家习惯一下，就它是一个新的参数。And what is a phase shift? So you can compare the two waves here and here. So you can see that the shape of your curve as a function of time are just exactly the same, but the only difference is the starting point of your wave. So if you take this one, if you take the plus a as the starting point for you to count, and you can see for the schematic diagram here, the starting point is here. So the starting point is shifted from the origin to the right hand side for a certain time, and this, we call it a phase shift. You can see that if you compare this one and this one, if you try to count, if you turn the major parameter for your wave into angles, you can say that the wave on the lower schematic diagram has a phase shift with respect to the original wave. 好，大家可以看一下上面那张图跟下面那张图， 就是呢，我们现在的参数是位置对时间嘛。然后呢，很多时候我们其实喜欢用角频率跟时间去做描述，我们喜欢用角度去描述这个问题。因为如果你去思考 cosine function 的话呢 ，cosine 0度就是正一嘛 ，cosine 派是负1，好，然后 cosine 2派你又回到0度。那我刚才说的那个0度派跟2派，我们会叫它相位角 （phase angle）。然后呢，你在上面这张图跟下面这张图，你会发现这两个 curve， 这两个震荡的 curve， 它们的形状长得是一模一样的。但是呢，下面这张图的 curve， 它往右手边就是 shift 过去一小段时间。那你也可以说它的相位角往右手边 shift 过去一小段。那一段相位角，我们会叫它相位差 （phase shift）。OK。好，所以这样希望大家就可以理解所谓的相位就是 phase 的概念。好 ，and then the second one here, this is why we care about period, because just as I said, so this is from +1 to -1 and back to +1, and here we start another cycle. Then you can see the cycle here and the cycle here. The curve, the shape of the curve are just exactly the same. So when you're writing the equations, and if you put a t into the bracket here, so this is the angular frequency, and this is the time. This is the parameter which is running. And if you just put another t into it, the shape of the curve are just exactly the same. So this is how you do it mathematically. And this is the reason why we call it period, because it's just simply related to the cycle of your oscillations. And a period is just equal to 2 pi, so this is the total phase, 2 pi divided by the angular frequency. And the frequency, this is the frequency that we're used to. So the frequency is just equal to 1 over the period, and this is the omega divided by 2 pi. So this is the phase, this is the angular frequency, and then normalized by 2 pi. We take 2 pi as a cycle. So here are many new parameters, and all of them are just related to each other.然后这些新的语汇有点难哦，是因为我们在位置跟角度两个世界中间跳来跳去，你有没有发现？就是我们有的时候我们在讲位置，我们有时候就突然跳进一个角度。好，我们会这样子跳来跳去，是因为等到你进到更高阶的应用之后呢，用位置去描述震荡有点烦，你会想要把它做一个傅立叶转换，你直接讲频率就好了。对，所以我们总是会不停地在位置跟角度两种观点中间跳来跳去。So I think if you are very observant, if you are very sensitive, and you just find out when we are describing everything, then we are jumping between two perspectives. One of them is we look at this thing from a positional point of view. And sometimes we switch our perspective. We start to look at it with angles and frequency. That is the reason why when we are dealing with the complicated oscillations, which is the superposition of a lot of simple harmonic oscillations, we like to simply say the frequency of the waves and phase of the waves, and we can do the Fourier transform and we can just describe it easily. So that's the reason why we always look at this from two perspectives. Okay, and then here's a little summary of the oscillations, and we just introduced the simple harmonic oscillations. And you can see that the most important thing is we introduce the frequency. Oh, and here's something about the physics, the physical meaning. You can see that omega is the angular frequency, and the frequency of your oscillation is actually determined by the mass of your oscillator and the elasticity of your spring. And sometimes we call the omega here, we give it a name, it's called a natural frequency. 好，然后那我们再回到物理，这边有一个比较重要的事情，你就会发现说 omega 这个参数刚才是跟时间绑在一起嘛，然后你根据观察那个 cosine function 的行为，你就会发现说omega 它其实是直接连接到你的振荡的频率。好，你频率越高，它的振荡就越快；你频率越低，它的振荡就越慢。那么呢，而且你还发现 omega 它是直接会连接到你的弹性、回复力的本身的弹性，然后还有呢，你的质点的质量其实就是惯性啊，一个弹性一个惯性。然后你要开一个根号。那因为这个震荡的频率呢，它太基本了，而且它非常的好用，我们给它取了一个名字，我们叫它自然频率 （natural frequency）。好，所以其实呢，以后只要你遇到震荡的问题，我们基本上都会想办法把它化约成简谐震荡的形式。然后等你找到了简谐震荡的 pattern 之后的下一步，就不要怀疑，赶快去找它的自然频率。So this is how you do the characterization of a oscillation. So whenever you see an oscillation, just try to simplify it into a simple harmonic oscillation, and then try to find the natural frequency. So that is the standard step to do the characterization. Then, okay, and here is okay. So we got the displacement, the x of t, and then it's easy to have the velocity and the acceleration. Oops, sorry. Here's a little typo. 我前这里有一个小小的错字，动到了。这样才对。Okay. Okay, so I think I don't need to go into the details, you can just check it out by yourself. And here is the important remark. So for the velocity, when the omega t plus phi, when the angles in the sine function is equal to plus or minus pi over 2. And then your sine function turns into plus 1 or minus 1. And that is the critical point when you have the maximum velocity. So this is how you get the maximum velocity. And pi over 2 is related to the position here, which is the equilibrium position. Yeah, so it makes sense. And then for the acceleration, when your omega t plus phi is equal to 0 or pi, so 0 or pi, so this is the point where you have the maximum acceleration. Okay. So you can see from the equations, and you can check if it satisfies the experimental fact. Yeah, okay, it makes sense. And you have to be careful when the omega is coming into the velocity and the acceleration. And then, okay, so then if we do graphs for the position, velocity, and acceleration, then you can see that all of them are cosine functions or sine functions. And basically cosine and sine functions, they are this. Actually, you can say that they are exactly the same thing, but with a phase shift. And you can see that when the x is started from the the positive maximum position. And now when it starts to run, so this is a cyclic motion, and for the velocity it started from 0, and the velocity is changing that way. And for the acceleration, then you can see that this is how it started and how it goes on. So actually you can see that they are the sine or cosine function with the same period, or you can say they are having the same frequency, but they have phase shift. So the velocity is a little bit slower. Yeah, it's slower than the position. And the phase shift is minus pi over 2. Right. And the acceleration, how about acceleration? You can say it is slower, or you can say it is faster. It depends on how you look at it. Yeah, but the phase shift is pi. Okay. And then we do the derivation for energy of the simple harmonic oscillation. So the kinetic energy is 1 over 2 mv squared, and we already have the function for the velocity, so that just put them into the equation, and finally this is what you have. And just remind yourself that omega is k over m, so if you have a omega squared, then that is actually equal to k over m. Then for the elastic free energy, elastic energy, 1 over 2 kx squared. Then you just put the x squared in, and then this is the function. Okay. And you can see that if you put the k and u, another typo. 对不起，这题我又打错字。Here you can put the kinetic energy and the elastic energy together. And if you put them together, you can see that the sine squared function and cosine squared function, if you do the summation of them, they just equal to 1. So the total energy is actually a constant. The total energy is not changing at all. And the total energy of the system is decided by the elastic constant and the amplitude. And you are the person who set up A. So you decided how big the A is. 所以你在这边你可以算出你的动能，你可以算出你的弹性位能，你把它全部加起来之后呢，你就会发现不管我在震荡的时候的哪一个瞬间，我的能量都是一样的耶，就它是一个常数。然后呢，你的总能量是弹性系数还有振幅决定的。然后呢，振幅是你决定的。好，就是振幅是你决定的，就是你把你的质量就是拉开它的 equilibrium position 一段位置，然后那段位置到底有多远，那是你决定的。Okay, so this is the total energy. And if we plot the energy as a function of time, you can see that the total energy is exactly the same. But if we start from, for example, if you have a spring and then you make it very long, and if we start from a point like that, so first you can see that this is 0, just a reminder. So this is potential energy is maximum, and then the potential energy is converted into the kinetic energy of your mass. So the potential energy is going down and the kinetic energy is getting bigger. And then you can see that this is the point when your kinetic energy is on the highest point, and when all of the potential energy is converted into kinetic energy. And then the conversion gets reversed. So the kinetic energy is releasing from your mass, and then all of these released energy gets stored into your spring again. And then here you can see the potential energy is getting bigger. So the kinetic energy and the potential energy, somehow they are cyclic, converting to each other. So this is why it calls oscillation. And this is the ideal system. We just first idealize that all the energy is conserved and the system is not coming out. Okay. Energy of the simple harmonic oscillator. Here's a summary table, and this is the crucial time point, position, velocity, and acceleration, and kinetic energy and potential energy. So if you need it, and then you can look around, and then you can keep it with you. And here's another thing which is related to physics. So you can see that we just checked the energy versus time, and now let's check the energy versus position. So now the horizontal axis is the position of your mass, and the origin of this coordinate is the equilibrium position. So you can see that if your mass is deviated from the equilibrium position, the potential energy gets higher, isn't it? And when your mass is very close to the bottom of the well, the bottom of your potential energy, the kinetic energy is in maximum. So you can imagine that now your mass is running back and forth, like it is confined in a well. So whenever you see a structure like that, then we can simplify that situation into simple harmonic oscillators. Then you can analyze it with your knowledge in simple harmonic oscillations. And the structure of potential like that, sometimes we just simply call it potential well. 然后大家可以看一下，就是这边是我们刚才有讲过你的能量对时间的变化嘛，前一张图。这边是能量对位置的变化，就是你的指点在equilibrium position 的时候呢，它的动能是最大的。然后呢，只要它偏离你的 equilibrium position， 在这一整个系统里面呢，它的这边是弹性位能，它的位能就会变高，然后呢，你的动能就会下降。然后你可以想象，所以你的指点，它就会呈现一种好像被框住，或是好像被 confine 的中文是什么？限制。对，你看起来就会好像，它好像被一个无形的看不见的东西，好像把它限制住了。然后那个限制住它的东西，其实就是一个固定量的 potential energy。那 potential energy 在中间是最小的嘛，然后你只要偏离你的 equilibrium position， 你的 potential energy 就会变大。所以我们很多时候在分析一些物理问题，我们就会先把它的位能的图、位能对空间的分布图，我们会先把它画出来。那你只要看到像这样子的结构的话，你大概就知道哦，那应该就会有震荡哦。然后呢，你就可以稍微再使用一些小技巧，对，有一些技巧。那你可以把你的问题简化成一个 simple harmonic oscillator 的问题。那因为它看起来很像一个井，看起来就很像你的指点被困在一个井里面，然后在里面这样子前后荡来荡去，然后他没有办法从那个井里面脱逃出来，因为他只要一想要上去，一想要从那个井喷出来，然后可是他本身的动能就会被转换成位能，然后它就会变慢，它就出不来。对，那所以这个时候我们也会讲这样子的位能结构，就直接叫它一个井。以后你听到大家讲说位能井的时候，就是在讲类似这样子的状况。对，那位能井也不见得会是对称的，它可能会是不对称的。 那么你在2维空间或3维空间里面，也有可能在某个方向上面它是一个景，但是在另外一个方向上面，你的 particle 有逃逸路线，就是它就可以逃走。好，问题就会变得比较复杂，会变比较有趣。好，所以这就是为什么我们常会讲未能镜就是因为你看着那个质点本身的行为的时候，你会觉得它很像被困住。好 ，OK， and here's an example about how to use simple harmonic oscillators in real cases. So if you have a molecule is a combination of 2 atoms. And the 2 atoms, they have chemical bonds between them. So, but you can sometimes we just simplify them into 2 particles connected by a spring. And then we can analyze the behavior of your molecules in the view of a simple harmonic oscillator. So, here the potential energy is generated by the electrons around the nucleus. So now this is the you can call it the electromagnetic potential. This is not the elastic force, but the action of it is actually just like a restoring force. So now it has a name which is called the Morse potential. Yeah, I think that's the name of the discoverer. And here the horizontal axis, this is the internuclear separation. So this is changed by the distance, by the equilibrium position of the 2 molecules. Okay. And what they do is they do oscillation. So this is not the same as the oscillation, the simple harmonic oscillation that I just showed. It's just, we just take the center of them, and the 2 molecules is oscillating this way. So, and we calculate the potential energy and we calculated the kinetic energy. So, okay. And we also used, we just used that force is equal to the dVdr. So this is a very classical point of view. And that just make it equal to m acceleration of the 2 particles. And then we can go on with the equations of simple harmonic oscillators. And you can see that in this kind of, the thing is, the actual potential energy is not symmetric. So this, this is not symmetric. So actually here, this is a little bit shallower, and it has a big tail on the other side. But if we try to fix ourselves in the position which is if we try to fix ourselves for the oscillation, which is not too big. So this is just slightly oscillating. If it's not a big oscillation, let's just focus on the small oscillation right now. So then it's like we are focusing on positions like here. And then we can more or less analyze it as a simple harmonic oscillator which has a symmetric potential. And then we can try to derive the energies of it. And then you can see that if you put the quantum mechanical constraints inside, and then you can find the energy levels in your potential well. Okay, so this is how we work on it. 我想在这里面呢，它最重要的事情是你会发现，在现实状况底下，对这个图，它是一个 potential energy 的图，主要是电子环绕着你的原子核，然后呢，那个电子的分布它会产生一个电磁场，然后那个电磁场里面其实就是它会有一些电磁能量，那个电磁能量呢，它们的分布方式会根据2个原子之间的距离而改变。 好，然后所以那2个原子的之间的但是你就会发现说，其实它的那个 potential energy 左右是不对称的。但是没有关系，我们通常在开始做这些事情的时候，我们喜欢把它简化成一个单纯的 case， 所以我们通常都会先从小范围的 oscillation 开始。那么就是它会有一个平衡点嘛，平衡点是 R1，就是2个球，然后它们的电磁能量最低的点，我们把它取名叫 R1。那如果说围绕着这个能量最低的点，我们先做一点小幅度的扰动，不要太大。那小幅度的扰动的话呢，至少在这一段，你可以近似的把你的 potential energy 看成是左右对称的。那你就可以先用 simple harmonic oscillation 先做一个简单的入门的快速的估算。然后呢，如果你再加进一些量子力学的考量，就是你的能量分配到各种不同振荡形式的时候，它不会是连续的，它会是一包的这样子。那么这个时候，你就可以在你的绿色的这个 potential well 里面，你可以找到能接。好，然后通常我们会是 simple harmonic oscillation 做出来之后，我们会再去修改你的模型，慢慢把它修正到说，如果我的 potential well 是左右不对称的，是不对称的时候，那么它会越来越接近什么样子？那你可以比较一下，就是在能量比较低的状态的时候，其实 simple harmonic oscillation 跟实际上的状况差异其实不会太大。那比较会有问题的是，当你的震荡幅度变得很大的时候，然后呢，你的 potential energy 并不是像胡克定律这样子呈现一种 linear 然后 parabolic 的状态的时候，那问题就会比较大。好 ，OK， so this is one of the case when you can so this is a graphical point of view. So you can see that we are analyzing the oscillations of the molecules as if they are two particles and connected by a spring. And when the spring is driving the oscillations, and we are looking for the modes of the oscillations. So first of all, we find the primary energy levels with the simple harmonic oscillator. And then if this is a molecules with simply 2 atoms. And sometimes when we have complex atoms like water, H2O, and we have an O and we have 2H, and here are 3 types of oscillation, isn't it? So you can see that here are asymmetric stretch, symmetric stretch, or the cute movement like scissoring band, isn't it? So then we can analyze that this is the primary state of the oscillations, and then we can get into it. We can try to analyze each special type of oscillations, and usually what we see will be something like the split of the energy levels. So originally it's a primary energy level, and somehow the energy level is split into several different little bands. Okay. So this is in reality. 好，所以大家就会看到这边是一个假设说你是只有2个原子的振荡的时候呢，就比较稍微简单一点，你可以把它简单的简化成一个弹簧跟质点的振荡。那么如果说如果我们再想的更多一点，就是如果说你的化学分子的结构非常的复杂，就是它的振荡不是单纯的这样子而已的时候，然后呢，这边有一个例子给大家看。就是你可能是水分子，然后因为它有3个成员，然后3个原子，它们就会开始变化出很多种不同的振荡形式。好，然后那么这个时候我们会发现的事情就是呢，通常你的振荡它会有一个家族，就是像这样它会有一个家族，那一个家族里面会有几种变化型。然后这些比较细微的变化型，它就会造成一个叫做能量能阶分裂的现象。好， 然后那这个就是我们通常在做一些原子分子物理，或是在做化学物理或者物理化学的人，尤其是做光谱学的人，他们就会用这个技巧去分析很多事情。台湾的那个诺贝尔奖得主李远哲，他的专长就是做这种实验。好 ，OK。Here's another, this is a quick example. So when you have a crystal, then sometimes we just model the crystal as a lot of particles connected with springs, and now you can see the connection of the spring is getting complicated. So here are many different types of the oscillations. And then we just, in cases of solid-state physics, and we care about the vibration of the lattice, and the vibration of the lattice is related to the propagation of light, or the propagation of electrons as waves, because light is electromagnetic wave, and actually it's an oscillating electromagnetic force, and the force is driving all the lattice vibrating, so that is why the light is propagating in your crystal. And when the electrons is running into your crystals, and we should treat it as a matter wave, and then again that is the propagation of waves in your crystals, and that is related to the resistivity or conductivity of your material, and which is very important for electronics. Something like conductors, semiconductors, and insulators, and all of them are related to the propagation of electrons in crystals. OK， 那这边也是，我就直接一直往下上课了。那如果说想要上厕所的、想要干嘛的同学，就直接去好，那这边也是特别说，我们在分析一些晶体的时候。然后呢，这是跟固态物理比较有关系。我们会把一个晶体或是一个材料，我们会把它化约成很多质点，然后那些质点是用小小的弹簧连接起来的。然后那个弹簧的连接方式就看你的晶格结构，就是可能是什么面心立方体、心立方、四角形晶体、六角形晶体，很多那是一个非常有趣的世界。对，然后呢，那么光是怎么样在物质里面传播的？我们建立的物理模型就是呢，光其实就是电磁波，电磁波其实就是电场或是磁场的震荡，电场跟磁场其实就是力啦。所以光在物质里面的传播，它实际上做的事情其实就是那个电跟磁的那股能量，它们变成力的形式，然后在上下拉扯、震荡你晶体里面的原子。好，然后呢，它的震荡的方式呢，就会决定说你的光是怎么样穿过一个物质的。好，这章算是我个人在固态物理里面我非常喜欢的一章，对，非常的有趣。然后那这个时候你就是也是一样，你要用 simple harmonic oscillation、damping oscillation 跟 force oscillation 的方法去思考说，那我的这团原子被我的电磁波这样子上下震荡的时候，它那个波会怎么传递？然后再来还有另外一个是电子在晶体里面的传播。那电子如果说你在一个比较微观，然后量子力学的范围里面的话，电子我们会把它当成是波来处理，就是物质波。那么这个电子的物质波是怎么样跟原子的物质波互相影响、互相 superposition 叠起来等等。然后，尤其是你的晶体是一个有周期性的结构，那有周期性的结构就会产生驻波。好，所以这个是另外一个题目。那么也是一样，就是我们电子在晶体里面的传播，我们也是会用 simple harmonic oscillation 或是用波动去形容它。那么这个就会影响到你的那个材料，它是绝缘体、是半导体还是导体？那这个对电子学就非常重要了。因为电子学它基本上就是把各种材料做一些排列组合，然后呢去调整它的导电系数， 然后呢，你就可以去，你只要有了半导体之后，你就可以做二极体；有了二极体之后，你就可以做电晶体；有了电晶体之后，你就可以开始做类比运算。然后呢，你也可以开始，那类比运算比较复杂，然后但是只要你有一个开关，比方说二极体好了，你可以打开那个关起来，那你就可以开始去做一些逻辑运算。好，所以如果电机系的大家，你以后是做元件的话，你基本上就会一直都在处理这些问题。好，我休息一下，等我一下。那这个是所谓的拉伸或者是位置上面的震荡。那再来下一步，我们要做角度的震荡，也就是摆，就是 pendulum。So we just finished the oscillations in terms of positions, and now we go on with the oscillation of angles in terms of angles, and it has another name. This is called pendulum. So, okay, this is how a pendulum goes. So now let's find the mathematical representation of the swing. We have a particle. The particle is attached to something with a string, and now we are analyzing it with the terms of the angles, and the angle is between the string and here is a reference line. We set the reference line as its vertical. You can see this is the angle. And here are two vectors showing you the two important parameters. And the length of the arrows is showing you the strength of the parameters. But more or less is the same as the oscillation of a spring. But now we are describing everything in angles. So you can see here is the angle for the equilibrium point. We have the maximum, and we have the maximum angles on the two sides. The positive and negative is showing you the direction. The maximum angular frequency is the maximum angular speed. This is not angular frequency, sorry. This is angular speed. The maximum angular speed is when your pendulum is passing through the equilibrium point, and on the two highest point right here, the omega is 0. And now the acceleration, the angular acceleration. So at the middle point, at the equilibrium point, this is 0. And here this is minus a, this is positive a, and you can see if you compare the directions, they are in opposite, and the oscillation here is playing the role as changing the directions. So this is how a pendulum goes, and now we are summarizing the equation of motion of a pendulum. So this is the schematic diagram of a swinging pendulum, and this is very big, but let's just take it as a particle. This is the mass of it, and the particle is attached to the wall with a string. This is the tension, and the gravity is pulling your mass. So actually this is the gravity which is driving your pendulum swinging, and that's decomposed gravitational force into two components. Into two components. one of the component is on the tangential direction. The tangential direction is with respect to the string here. So this is a tangential direction, and the other component is in the same direction as the string. So this is going this way. And you can find the magnitude with the angles. So the tangential component is the mass, the gravitational acceleration, and sine theta. So you can see I'm sure you can see the geometry by yourself. So you can do a little bit of analysis here. And this is cosine theta. So I think this is okay, this is easy. You can see that this is the normal line, this is a reference line, and this is the direction of your gravitational force. And because they are parallel to each other, so actually the theta here is just equal to the theta here. So that's the reason why. Okay, so now we find the component of the forces. Okay, so now the force which is driving the pendulum swinging is the tangential component. So F tangential is equal to the mass, the tangential acceleration. Okay, so I think this is a key point. From the graph, you can see Ft is equal to mg sine theta, and the negative sign is showing you the direction. We set the direction to the right as the positive direction, and to the left this is the negative position, and this should be equal to m_at. And at, the acceleration on the tangential direction, is the second derivative of s. S is the path of the swinging track. So this is a track of the swinging particle, and S is just I should say S is the length of the path that it just go by. And S, you can convert it into the length of your string multiplied by the angle theta. So S is equal to L theta, and the second derivative of S is this one, because L is not changing during the swing, and the only parameter we change is the angle. Okay, so that is why we have it. Then you can put this term into the original equation, and you can do a little bit of arrangement. You can see that this is the second derivative of your of the angle, and it's turning. Okay, we have to do some trick later, but you can see that we have the coefficient. This is the gravitational acceleration, and this is the length of the string, and here's the sine theta, and you can do a comparison. So this is the pendulum system, and this is the spring system. Though one of them is in the this is in the polar coordinate system, and this is in the Cartesian polar coordinate system. But if you look at the structure of the mathematical equations, then you can see that they are just in the same form. And if you restrict yourself in small angle oscillations, so the sine theta is not very far away from theta itself. So that's the reason why sometimes when we have the pendulum, when the pendulum is swinging in a very small angle, and then we can just analyze it as, we can just simply take sine theta as theta. And experimentally, the angle should be smaller than something like 5 degrees. So this is what we see in the lab. 那大家可以看到的是，对单摆而言，你会看到一个角度的2次微分。然后现在右手边你的 term 是一个 sin theta。那如果说你稍微自我设限一下，就是你的 theta 如果很小的话，那 sin theta 跟 theta 本身的数字，就是那个数字，如果你用的单位是 radian 的话，其实不会相差很多。好，所以那我们会做一个小角度近似，我们就把 sin theta 当 theta 处理。那我们在做实验的时候啦，我们有稍微测试一下，就是小角度近似在什么范围以内适用。就是你的那个 theta 在180度的那个，在360度的那个系统里面，最好不要超过5度。超过5度的话就不太行。对，那你在5度以内的话，小角度近似是 OK 的。好，那么呢 ，OK， so now we are doing a small angle approximation, say several degrees. Then you can see that the simple harmonic motions, and we have the equation of motion for the pendulum. And you can see that actually the form of them are just symmetric. They're just exactly the same. So we can just apply the same knowledge. We can just make the same ansatz. So we can take that theta. It should be a amplitude, which is in theta maximum, the maximum theta. And we have a cosine omega t phi. Okay, so this is why we have the equation like this. And now the angular frequency omega is equal to g over L. So this is how we get the natural frequency of a pendulum. And if you would like to know the period, then you just convert it. Okay. And let's do a comparison between the two systems. On the green shade, this is for the pendulum, and in the blue shade, that is the spring system. And let's look at the period of them. So in the pendulum system, the period is related to the length of your string and the gravitational acceleration. And for the spring system is related to the mass and the elasticity. So sometimes it's a little bit confusing, but okay, I think this is kind of interesting. The period of your pendulum is not related to the mass at all. So sometimes it's a little bit counterintuitive. 对，这个通常大家会拿出来讲，觉得蛮有趣的地方，就是单摆它的振荡频率呢，跟质点本身的质量没有关系。对，这个有一点反直觉，还蛮有意思的。那实际上会影响单摆频率的是长度，就是你的单摆有多长，然后还有呢重力常数会改变单摆的频率。Okay, good. So that is the natural frequency of a pendulum. And this is an experiment. Experimental proof.
And I'm going to demonstrate to you that within the uncertainty of the measurements, that I get the same numbers in all three cases, within the uncertainty. So, if you're ready for that, you see here the timer, all of you can see, and here you see the pendulum, and I have two marks on the floor here. If I hold the bulb here, then it is 5 degrees, this is 5 degrees, and when I hold the bulb here, it is 10 degrees. Timing is not easy. The best way to do it is to start the timing when the pendulum comes to a stop. That is rather well defined. And then you let it swing 10 times, and then when it comes to a stop, you stop it. And it would help me if you would count how many oscillations we have made. Because then I don't have to look at it. All I have to do is when I come close to 10, I have to watch for the moment of stopping, and then I will end it. So, we'll do this first at 5 degrees. I'm going to start it when it comes here. Yeah! Okay, now you count. You're doing very well. You're going to pass this course. .7, so that becomes that t. That means this whole equation now has to be divided by 10. And now you will see why I measure 10 oscillations. So t is going to be 4.57 plus or minus 0.2 divided by 10. That is plus or minus 0.02 seconds. And you see, comfortably within the prediction. So maybe my reaction time is a little better than 0.2 of a second. Don't count on it because you haven't seen the rest yet. So, now 10 degrees. That moment is crucial. That moment is crucial. That's where you can lose 0.4 of a second and then you look like an idiot in front of your students. Now comes the hardest part. The hardest part is that we have to change the mass of this object. And the way that I'm going to do that is prominently demonstrated on the cover of my book. Yes, I'm going to hang on that pendulum. It is a difficult demonstration. First of all, it is painful. It really is. Second, the timing is tricky. Because when you look at a pendulum and when you see it stand still, you know that's really well defined, plus or minus 0.1 second. When you are swinging yourself, however, then you can only do it by sensing the moment that you think you stand still. And that's what I will do. And then you will do the counting. And this is very unpleasant. It is. something else I haven't told you. If you're a good physicist, you will say, if you're going to sit on that bulb, then effectively you bring the mass of the bulb up, and so the length of the pendulum will shorten, and so you get a shorter period. And I know that too. Therefore, I will have to stretch my body so that when it is here, that it is almost completely parallel to the floor. If I don't do that, I will not be able to convince you that the period is independent of the mass. And that makes it very difficult for me. So I will start it at some moment, you will see when, and then you do the counting. Are you ready? Okay. Yeah! You count! This happens sometimes. And in fact, nobody knows why. Have to start all over. I did not stop it, I really didn't. Oh, it's still counting? Okay, I have enough energy to give it one more attempt, but not to give it two more attempts. Okay. You ready? Okay. Oh, this really hurts. Can't you count a little faster? T. With Walter Lewin. What is it? 45.9 plus or minus 0.2. Period is 4.59 plus or minus 0.02. I told you, physics works.
This is a 有趣的实验，so this is an interesting experiment. 搏命演出。Okay, so here's another experiment. So do we have enough time to watch it? I don't think so. But this is an experiment showing you that the conservation of energy. And that is represented by the height of the ball. So if you are interested, you can watch it by yourself. But for the rest of the 20 minutes, I would like to finish this lecture. So, okay. we just started with the simplest pendulum, but what about the swinging of objects with arbitrary shapes? 所以我们就是刚讲完一个单摆，就是一条线跟一个支点嘛。那假设说你现在要分析的物体是它的形状，就是随意的，它就不是一个传统意义上面的单摆，它就是一个拥有一个很奇妙的形状，然后打一个洞，然后就钉在那边，然后它就开始摇摆。这时候你要怎么办？这时候你怎么办 ？So here's a freestyle pendulum, but you can just start with analyze. Just try to look for pivot is something that you decided. 所以你的这个摇摆，它的支点，这个应该就是一目了然嘛。所以通常都是你自己决定的。And then let's look for the center of mass of your arbitrary object. So this is the center of mass. And you have to find the distance between your pivot and your center of mass. So now this is the distance between them and this is D. So now you can simplify your system as you can just take the position of the center of mass as the places where all the mass is on it. So you can take it as a particle right now. And then you just follow the position of your center of mass. Then you find the path of your swing. Okay. And here, now we put this is the gravitational force. So you can just put your gravitational force just equally effectively on your center of mass. Right. And here is we just try to find the torque on it. So now we are using the torque to analyze it. The torque is the M, the gravitational force, and D. So D is for the arm, and mg is the force, and sine theta is how you take the tangential component of your force and convert it into torque. Now you can see that the total external torque on it is this one. We just derive it, and this should be equal to your moment of inertia, 转动惯量, and alpha. So this is angular acceleration, and angular acceleration is just equal to the second derivative of your theta. So theta is the angle here. And now again we come back to a position like we have a partial differential equation. Second derivative back to theta. And mgd over I, this is the coefficient which is related to your frequency. Okay, so now we can just use exactly the same ansatz. The only difference is the natural frequency. Now it's turning into mgd over I. And now then it's your task to find the m, to find the d, and to find the moment of inertia. Then you get it. 好，所以那么大家应该可以看出来哦，就是你就算你的摆动的物体它的形状是不规则的，那么你不要担心，你先找到它的质点在哪里，然后呢，你就可以把它等价的把它看成像一个单摆。只是呢，你现在所谓的质点的位置就是你的质点，然后它的 total mass 你就放在你的质点上面。那重力的部分也是，你就把它当做说我所有的重力都是施加在我的质点的那个位置上面，然后再来你就可以使用力矩跟转动惯量的概念，你可以下去做推导。很快的你就会发现呢，也是一样，就是你的角度微分2次之后会变成角度本身。只是呢，现在你的关于自然频率 natural frequency omega 的地方呢，里面的参数就变得复杂了。但是不用担心，你只要去找出来说我的 total 质量是多少，我的 G 是多少，我的 D 是多少，然后还有转动惯量是多少，你一样可以把你的 natural frequency 就把它算出来。Good. And here's another example. So if you have a rod, if you have a stick, if you fix it on one side and when the stick is swinging, then again, here's just another example. Just take this one So this is the partial differential equation, and this is our solution. Now the thing is, what is I? Okay, so in a rotation like this, the I is 1/3 mL squared. We just derive it in the problem solving session, so you can just apply it. And D, now it's just exactly at the center of your rod. So this is how you get the period of your swing. And here's another example. So this is called torsional pendulum. So we just analyze the swing. And now if just the twist, if now we are analyzing the twist and the twist is sort of oscillative. 那这个叫扭摆。就是呢，在很多机械工程的元件里面会用到扭摆。那扭摆其实它的基本型就是这样，就是它会有一根绳子或是柱子之类的东西，那你下面会有个圆盘，然后这个圆盘它是水平的，然后这样子扭，然后那个扭有时候它也会呈现出一种震荡的状态。那个震荡你要怎么样去分析呢？ So again, now we should apply torque, and here is a relation to describe the twist. So the torque is equal to rigidity multiplied by the theta. So this is the Hooke's law for a twist for arbitrary deformation. 所以这是你可以看到这里是它的力矩等于刚性系数乘上角度，那么就胡克定律它其实不是只有直线性的运动的使用，很多时候那个扭转或者是弯曲，然后或是各种奇妙的形变，我们其实都可以用胡克定律去做替代，差别只是在于说你的那个弹性系数呢是什么东西，你要怎么量。好，那我们这边我们可以使用的就是刚性系数。Then again, now we just take that the total torque is equal to moment of inertia and alpha, angular acceleration. And then we come to the second derivatives, and then we can get the natural frequency. So the story is just the same. The only difference is your parameters. 那我们很快速的走过这3个例子，你就会发现，就是就算形状改变，就算运动的形态改变，但是呢，我们只要是在比较小范围，然后在回复力是位置的，只要回复力是正比于位置，好，就是它是一个 prerequest。只要是在这样子的状况底下呢，几乎大部分的状况啦，都可以顺利把它简化成一个second derivative， 就是2阶的偏微分方程式。然后呢，你一样可以在那个2阶的偏微分方程式里面找到一个震荡的 pattern。那个震荡你可以再深入一点，你可以去找它的自然频率。OK， 好，所以大家希望这样子就可以了解说为什么简谐震荡它在物理学里面很重要。就是其实我们可以，它无敌啦，基本上就简谐震荡是无敌的，就是很多复杂的状况，其实我们都可以把它化简成简谐震荡。And then here is another question. So we just fix the pendulum in 1 dimension, but in reality, of course, it's going to be at least 2-dimensional swing, isn't it? 就是那假设说我的单摆是我们刚才就是一定是在一维上面先处理一下这个问题，但是实际上你观察真正的 pendulum 的时候，你就会发现它不会是只有1维的震荡，它会有2维的震荡。那这个时候呢，它会发生什么事情？那这个就会叫做利萨鲁图形，就是你会发现，在 x 轴上面的震荡跟 y 轴上面的震荡，它们的频率不一样的时候，它会产生各种不一样的图形。So your oscillation, if the oscillation on the x direction and on the y direction, if they have different frequencies, and the differences between the frequency will change the patterns of your swing. So that is another topic in signal analysis. So in the very old time, when you are using the oscillators, and usually we just have a electron gun, we have only one channel, but if you have two signals to be analyzed, and then you have to put it into the same channel, and that is the time when we are using this pattern to find their frequency and their phase shift. And so that is very useful when you are using oscillators. But now usually we are using digital oscillators, and all of them are managed by the electronics, and we have multiple channels. So now we don't use that technique very often. 这个利萨卢图形其实是在早期你的 oscillator 示波器。就是比较早期的示波器，它其实是一个电子枪，然后呢，它就是那个电子枪的电子喷出来以后，然后它会就是照在一个涂了荧光物质的玻璃上面。那你看的就是那个荧光物质的轨迹，你就可以大概知道说，你用那个形状去看你的电磁波的波形，或是看你的电流或是电压的波形。可是因为早期它的那个示波器都只有一根电子枪，然后呢，可是你现在偏偏你有至少2个信号要输入进来，你要分析它们的频率跟相位差的时候，那就很麻烦嘛，因为你就一根电子枪，这时候你要怎么办呢？你就是你就用 X 轴跟 Y 轴，然后输入2个不同的信号，然后你就去观察这个利萨罗图形，你就可以从利萨罗图形上面去判断说，那我的频率是2个 channel 的频率格是多少，还有我的相位差是多少。但是因为现在就是比较现代的示波器都是数位型的，而且它会有好几个 channel， 然后我们就是很单纯的把信号输入进去，然后每一个信号都有它独立的一个电子电波，可以去做一些放大啦、缩小啦，或者是修波形等等的工作。而且我们现在那个电子元件处理的速度都很快了，所以很多时候我们甚至有一些示波器是有4个 channel 可以同时跑的，还可以一边跑一边做傅里叶分析。那我们就比较现代的应用上面就比较少在使用利萨罗图形了。好，所以也是一样，就是有兴趣的同学，你们可以去看一下所谓利萨罗图形，就是早期的博物实验很喜欢做这个啦，对，但是实际上在实验室里面我们很少在用。好，那我们最后可以再来把这个影片看完，3分钟应该可以。So now we can watch this video.
I have here a pendulum. I have an object that weighs 15 kilograms and I can lift it up 1 meter, which I have done now. That means I've done work. MGH is the work I have done, believe me. I've increased the potential energy of this object. 15 times 10 is about 150 joules. If I let it fall, then that will be converted to kinetic energy. If I would let it swing from 1 meter height, then you would be there and it would hit you, you'd be dead. 150 joules is enough to kill you. They use these devices, it's called a wrecker ball. Then use them to demolish buildings. You lift up a very heavy object, even heavier than this, and then you let it go, you swing it, thereby converting gravitational potential energy into kinetic energy, and that way you can demolish a building. You just let it hit, and it breaks a building. And that's the whole idea of wrecking. So you're using then the conversion of gravitational potential energy to kinetic energy. Now, I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here it could not be higher There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed where I stand here. I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it 0 speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0. Physics works, and I'm still alive.
Okay. 好，那我们今天so we just finished the lecture today. Next time, that is the hardest part.
Spike Theater presents.
下一堂课就是超难的。
有问题想要问？
好，等我一下。
好。刚才在讲未能景的前几页有提到这个，对，就是为什么是这里是2/2？就是周期的话是如果是用那个弹簧震浪的话，周期是过去再从中间那个静力平衡地方过去再回来再回来嘛，所以就变成应该会经过未能最大的点1次2次嘛。哦，对，1次2次。等一下，所以这个图是从最顶端，就是这边开始放。对。哦，然后再回到这边。对，哦，那就没有问题了。
好，那就没问题了。自己弄清楚。好。
等一下，好像也不太对。
对啊，好像不太对。
因为 K 最大的点会是在哪里啊？
中间点。
K 最大的点是会是在中间。
对，那这样的话，
就是它应该会
在中间的话，应该好像不会是t 的时候。
我看一下，周期应该是no， 我看一下。
而且等一下而且看到左边的时候，位能也是最大，所以应该是1次、2次、3次，对不对？
周期是从这边开始，这样过去，这样回来，这样叫一个周期。然后呢，位能最大的时候，就是弹簧拉的最长的时候。
位能最大是弹簧拉最长。
对，所以弹簧拉的最长的时候，到弹簧变得最短的时候，然后是1/2周期嘛？
是4/4周期。
是吗？
最短。
就是弹簧最长的时候，这是弹簧最短的时候，然后弹簧最短的时候，又再回去最长的时候。
这样是半个周期。
这样是一个吧？
就是这样是一个就是
因为现在有一个问题是，这个0好像不是弹簧最短的时候，因为弹簧最短的时候也是位能极大点，因为位能的0微点是在回年静力平衡的
对，没错，
对，所以应该要是这里是t，这里
对，
对，没错没错。
对，那好像有你，要不然我就
当然是他
你也可以出的哦。
这样。
原来是这样。
对，好，对，这样没有错。好，谢谢。
我还要问一个就是前几点。
好，
就是这个东西它是有正负吗？
有，
它是哪边的正？
看你以哪里为基准。它没有，就是看你以哪里为基准。如果你选择 origin 为基准的话，
对，
往这里就是正的，往这里就是负的。
那出来的话，假设这个是正的话，那出来图形应该就是往左移。
如果是，但是等一下要注意一下，加正的话呢，
加正是
对，那会变成你画出来的图其实是要往这里。你画出来的图就会变成起始点是在这里。如果你的这里是正的话，你起始点就会是在这个地方。
而且我还有一个
对，没错。所以加正的话，你的图你应该要往那边移过去。
所以我们会说这个图的它的 shift 是
就是如果说，我想一下，
你放弃了？没有，我放弃问你。等下我自己也要回忆一下。我看一下这个。
我在公式里面，我想要保持它 phi 是可正可负的弹性啊。如果你的 phi 是正的话，可是我在这里写一个负拍也不对，也不对。
对啊。
对，所以我觉得你就放在心里面好不好？你就是这个 phi 是正的还是负的，它就是一个有弹性的。
phi 可以一个图的 phi 可以是任何就是可以是 phi 加2拍，也是它的
phi。phi 什么叫 phi 加2拍？
就是假设
phi 加2拍没有意义，应该说 phi 会被限制在。
就是 phi 有一个限制，就是
对，其实 phi 有一个限制啦。
你的 phi 如果是加2拍的话，你就从这里 shift 到这里了。
但就是没有意义，因为就变成一开始的相位，
你就等于没有飞，
就等于没有相位。
所以一个图的 phi 可以有很多个。是这样
phi 不是一开始就固定了，就是其实跟起始位置有关。
就是你的波，你画出一个波来，它每个波就会有一个自己的 phi。
就有个自己的 phi。其实他们可能长得一样，但是他们可能是不同的。
就是你的 phi 在改变的时候呢，你就是这个波的形状维持不变，但是它可能是从这里开始，也可能是从这里开始，看你的 phase shift 是多少。嘿，对。
我还有最后一个问题，就是从这里到这里很直观嘛？
就它，end 出来之后就变成啥？
就是可以把它当做把质量缩在质点这一点去算。有什么看？就是因为我其实没有办法。
没有，我用这里拧过来，跟 end 过来。
只有就是
就是不是。它过去是什么不重要，
所以这中间没有什么推导，就是。
推导主要是在图上吧。
它0.1的差。
你也可以，你想弄的话，你也可以用微积分啊，就是不是，但是你最后得到的答案就会跟质点是一样的。
就是我们就先这样写就对了。
也不是先这样写，就是这段
就是已经有人推导出来了。
就是从tau ext I alpha， 然后是质点，我看一下，
可以把质量说的
啊，就平行轴定理啊。去哪边提？我不知道，我看一下。
平行矩也是 I 才可以用平行轴，力矩也可以用平行轴。
没有，不是那件事情，就是我知道你想问什么，那你想问的事情，我们在推导平行轴定理的时候已经推导过了。对，这个是我
就是可以用相同的方法去推。
我 sense 得到你想问什么，虽然你讲不出来，但是我们我那段故事我们在平行轴定理的时候已经讲过了，你可以回去复习一下。 对，好。
你上课都会有影片传上去吗？
因为我之前那个什么，
我的话，我们有一个那个直播的 channel， 所以你可以去上直播的 channel 去看影片，我都有录音。对，
怎么了？
老师，那个上礼拜五就是那个看电影的那个那个是什么时候才要写那个题目？什么时候才会上传？
我没梗了，我想不到。
还是只有大写心得，写心得。那心得的话要早一点，不然都快忘光了。
好，就写心得就好。好，就写心得。好，我晚上我再去 post。对啊，因为我真的无言了，我没梗，我不知道要问什么。
有点慢到了。
不抛什么，都家人都。